Welcome to our NPTEL lecture series of flexible AC transmission system device. Today we shall continue our discussion on the series fax devices. This will be our last lecture on the series fax devices. We were discussing on a previous class on TCSC operation. This is also discussed, but we wanted to recapitulate also this phenomena. That that the time duration of the voltage reversal depends primarily on the XL by XC ratio of this TCSC and also the magnitude of the line current. And for this reason, if this logic is satisfied, that when XC is much greater than XL, then the reversal is almost instantaneous. And what happens then? The periodic voltage reversal produces a square wave across this capacitor. So, this will be the superimposed, this is the TCR voltage and this is the VCO without TCR. So, this will be the superimposed voltage across the capacitor while TCR. So, what has happened? The periodic voltage reversal produces a square wave across the capacitor and that is added up the sine wave to produce a line current. So, for this reason line current will be the same fashion. The steady state compensating voltage across a series capacitor comprises uncontrolled or the free running part of the sinusoidal waveform, that is uncontrolled sinusoidal waveform, and a controlled component of the square wave, that is this part, and that both will add up and ultimately produce the Vc that will be a function of alpha. Generally, the square wave magnitude is controlled through the charge reversal of the TCR, and for relatively small value of XL, the inductive inductance. So, time duration of the charge reversal is almost is not instantaneous, but it is quite well defined by the natural frequency, and that is the frequency, that frequency is given by 1 by under root of LC for the TCSC circuits. Since TCR conduction time is approximately equal to the half rate of the corresponding frequency, then it will be T by 2 equal to 1 by F. So, what happen? If XL increases related to XC, the conduction period of the TCR increases and the zero crossing of the capacitor voltage become increasingly dependent on the line current. So, you cannot change this capacitor voltage as you wish. On the other hand, for this we should have a less value of the inductive reactance. Small XL is advantageous and in providing the well defined charge reversal, control of the period, control of the time period and corresponding to the compensating voltage. This is essentially this reactance acts like a electrical inertia, inductive reactance. So, it does not allow to the change of the polarity of the capacitor, which is required for the actually successful operation of the TCSC. On the other hand, small reactor is advantageous. Why? It facilitates or facilitating the effective protective bypass of the large surge current in case of the system fall, and also it requires for the DIDT protection. But small XL, what does it do? There is a demerit of it, increases the magnitude of the current harmonics, since it will allow the current to flow and thus harmonic content will be more generated by the TCR and circulated to the series capacitor. Therefore, it is also introduced harmonics in the capacitive voltage and the ripple will be there in the harmonic voltage due to this harmonic current. And apart from it, this small inductor also decreases the actual there is a overlapping ambient called mu. You have studied into the effect of the source inductance in case of the power electronics converter, range of the actual delay angle control, and thus it is possible to make closed loop parameter regulation more difficult, because there will be a current which will decay for the ongoing thyristor, there will be a current for outgoing thyristor. So, there is a overlap angle that is called mu. In case you have studied in the power electronics in case of the source inductance, same principle is applied here. Generally, the value of XL and XC ratio for practical TCSC would like to be 0.01 to 0.03, 10% or 30% in range, depending on the practical requirement and the constraint. We shall discuss in our final discussion some kind of case studies, there we will find it out how the limit has been chosen. It is important that the natural resonance frequency of the TCSC. So, you know that actually if inductor is little more, then it will oscillate in the natural frequency of oscillation. So, we have a constraint on the natural frequency. Our TCSC does not coincide or close to the 2 times or 3 times of the fundamental, then triplet harmonic will be actually a dominating factor. Mechanism of controlling DC offset by charge reversal is required to be increased frequently. So, that is something we have to keep in mind. And for ideal consideration, let us consider the ideal case. Instantaneous voltage reversal is assumed. So, that actually value of the XL is very small, then we can actually use this TCSC more better way. Then what we can do, initially the TCR can be gated on 90-degree phase shift, that is alpha equal to pi by 2, at which the TCR current is 0 because it is lagging by 90-degree, and the capacitor voltage is entirely due to the line current. So, that is the advantage. If it is very small, you can change the polarity of the capacitor at your will. And to produce the DC offset, the periodical repetitive of the gating sequence in the second cycle is advanced by a small angle eta. We will see to it. That means the prevailing half period is reduced by the actually by the proportional angle of eta to pi minus eta, that becomes the new conduction angle. And this action produces a phase advancement of the capacitor voltage with respect to the line current. And what happened due to that? As a result, the capacitor absorbs energy from the line, charging the capacitor at a higher voltage. So, real power will flow, and thus it will actually swell up the capacitor voltage. For this reason, the phase advance is maintained and it is actively controlled, so that capacitor voltage does not go to the very high value. Then the offset voltage of the capacitor would keep increasing. So, this is the way it has to be actually maintained. So, see that what happened. So, this is a line current and there will be a 90-degree phase shift. So, the TCS controlling signal. So, this is actually pi equal to alpha and this is pi. Then you have a normal operation of the thyristor, normal operation, and this will be the pattern of the voltage across a capacitor. But then you give a delay angle. So, actually it will pick up this voltage and the conduction angle is been reduced to actually eta times. So, now conduction angle is pi minus eta. So, what happened then, you have triggered here and it will conduct till pi, and then again you have actually given eta plus pi in this half cycle. So, what happened, gradually you will find that DC offset voltage get increased. So, this is the problem, voltage of the capacitor will swell up, and this amount where the amount you have put into the TCSC. Then how can you reduce this DC offset? Mechanism of controlling the DC offset by charge reversal, and it decreases. So, you have added actually conduction angle to some other level. So, you can have to add to the other polarity also. It is opposite process, that is when the magnitude of the capacitor voltage decreased by returning the periodic gating from the current 0 until desired offset reserve is desired. So, you have to wait till that time, then only you trigger it, and this way you can compensate a DC offset. So, this is the case. Let us assume that this is the same line current and you will give a trigger at 90 degree to it when it is at peak. So, what happened here change occurred for alpha equal to pi by 2, and it will have a conduction and it is already have the offset. Now, what happened? You can see there is offset. So, due to that. So, ultimately you got a DC offset here. Now, here you make it pi, and thus again it will carry the offset. To negate the offset, here you have to make the conduction angle pi plus eta, and here you have to make the conduction angle in this configuration negative sequence pi minus eta. So, then it will actually reduce the offset, ultimately voltage becomes sinusoidal. In that way actually offset of this TCSC can be removed. So, let us conclude it. So, what are the operation of the TCSC? So, therefore, continuous variable series capacitor compensation can be achieved by TCSC circuit structures. So, we can see in that it can compensate the power. That is, the effective capacitor impedance of the TCSC can be increased above the actual reactance of the capacitor bank by increasing the conduction angle. This is one of the prevalent features of the TCSC. And what happened then? This increase of the effective impedance due to the additional voltage the TCR produces across the capacitor by repetitive reversal of the capacitor voltage of the Vc. The current in the reactor is supplied from the parallel capacitor. Thus, what happened? The capacitor voltage will change in proportional to the integral of the reactor current, and reversing polarity from negative to positive by end of the conduction period. So, this is a TCSC characteristics, VI characteristics. So, this is actually the alpha minimum. So, you have a maximum compensation, inductive compensation, and this is alpha 0, and this is the I max, and this is the way you can limit, and this is for the case for alpha you can make it 90 degree, and gradually, and this is the limit for alpha c. The compensating voltage versus line VI characteristics of the basic TCSC is shown in this figure. In the capacitive region, the minimum delay angle is C min, sets the limit for the maximum compensating voltage up to the value of the line current of I min, because there is no inductive current, and at which the maximum rated voltage of Vc max, this is the Vc max, constrain the operation until the rated maximum current I max each reach. So, this is the thing. So, it will reach at I max, and so this curve will be followed for and it will reach to the I max. But you can actually make it alpha equal to 90 degree by inductive operation, and then this is the way you can reach. In the inductive region, the maximum delay angle is I alpha mean limits the voltage at the lower voltage at low current and the maximum rated of the thyristor current at high and at high line current. So, this is the limitation of it, where this is the slope of I mean and this is the case of alpha equal to 0, it will be limited by the I max value of the devices. So, if you can combine these two, so what will be the losses? So, the loss as a percentage of the rated VAR output is been plotted in this curve. So, what happened? The output versus the line current for the voltage compensation mode in the capacitive operation region for maximum and the minimum operating voltage as well as the bypass operation, it has been shown. The loss are entirely due to TCR. So, you can see that loss are due to intrinsic TCR, because there will be switching losses which include the conduction as well as the switching losses of the thyristor valve of the I square losses of the intrinsic resistance. So, loss will be entirely for the TCR. This is the case. So, if it is running in a impedance compensation mode, then it is applied to maintain the maximum rated compensating reactance at any line current up to the rated maximum line current. So, that what happened, it is same I alpha and this is I alpha mean and this is for alpha equal to 90 degree and this one is basically alpha equal to alpha C mean. So, it is a minimum alpha for the capacitor. So, see that losses how it will increase. So, this is the value of the C max and this is the value of the C min. So, changing the capacitor will actually according to the value of the I, this value will change. So, that the C min, the maximum capacitive reactance can be maintained at the below of the maximum rated line current. Moreover, the loss versus line current characteristics, because you know that there is a loss predominantly on the TCR, characteristics for the operating mode for maximum and the minimum capacitive compensating reactance is been shown here. So, this is for XC max and this is for this line for the XC min. So, we can say one thing, that voltage and the impedance compensation mode are interchangeable in control action. So, we can use actually either of them and it can be switch over to the one mode to another mode very easily. So, what are the drawback of the TCSC? The TCSC design is complicated by the fact that the internally generated harmonics aggravate the limit condition and mostly it arises from the TCR. The harmonic current cause additional losses corresponding to the temperature increases both thyristor's valve as well as the reactor. The harmonic voltages they produce across the capacitor increases the crest voltage and the stress of the TCSC power consumption and the voltage ripple in the capacitor. So, let us discuss the control of it. Function of the operation or the internal control of the variable impedance type compensator is to be provided with appropriate gate drive for the thyristor valve to produce the desired compensating voltage or impedance as per the reference. The reference to the internal control is provided by external voltage loop, external whose function is to operate the controllable reactive impedance so as to accomplish the specific compensation objective of the harmonic of the transmission line. Thus, what happened? External control measures these parameters line impedance, current, power or the delta angle reference within a measure system variables and then derives the operating reference of the internal control. Let us see that. And power circuit of the series compensator operated by rigorously synchronizing line current conduction and blocking control. So, you have to sense the line current. So, their signal is very much needed and it is sourced as a reference. It is not only define their effective impedance at the power frequency, but also determine their impedance characteristics in the critical subsynchronous frequency band, because you know that actually there might be a natural frequency of oscillation. So, you have to tamp out the subsynchronous frequency. Internal control include conversions of the input reference into the proper switching instances or the switching logics, which results in a desired valve conduction or blocking interval, that is we have to control alpha, measure the alpha, sigma, etc. And internal control is also responsible for protection of the main power components like valve, capacitor, reactor by executing current limitation or other protective measures. Structurally, the internal control for the 3 variable impedance by the compensator are definitely we have discussed all, that is GCSC, GTO controlled switch, TCSC and TSSC, and these are all almost similar, because this we require to measure the current, voltage and from there maybe phase angle and the power, and from there we require to find it out desired getting signal. Their function is simply to define the conduction and the blocking interval of the valve in relation to the fundamental component of the line current. So, this is the way it operates, and this valve do 3 basic functions. One is synchronization of the line current, this acts as a PLL in this case of the TCSC, and it controls the turn on and turn off delay. Mostly in GCSC it can control turn off delay also, turn on and turn off delay angle computation and gate firing signal generation. So, let us see that what is the internal scheme for the GCSC. Because of the duality between the shunt connected GCSC and the series connected TCR, the control scheme is totally analogous to the TCR and has 4 basic functions. That is, you require to have a synchronous timing provided by PLL, provided by the phase lock loop of the circuit that runs in synchronization with the line current. The reactive voltage or the impedance to turn off delay angle conversion according to the relationship discussed. Determination of the instant to the valve turn on when capacitor voltage becomes 0. This is an extra constraint it has been put. So, those are not available to the other 2 shunt compensator. This function may be include maintenance of a minimum on the time at voltage 0 crossing to ensure the immunity of the subsynchronous impedance. Generation of the suitable turn off and the turn on pulses for the GTO valve. So, this is the internal control scheme of GCSC, and it is almost same for the other, but in GCSC, so turn off logic also you require to compute. So, this is the VC reference, from there you can sense and you have a current, from there you got a PLL, and thus theta comes out, voltage to turn off delay angle conversion, and you get basically Vc lambda is a function of kFy, where actually that will be delayed by some angle, and this is basically the capacitor voltage sensing and the processing kit. So, from there it will be compared, and this is essentially to calculate what should be the delay angle or the firing angle or the turn off time of this GST. Now, as I told you, these methods are almost same for TCSC and TSS. So, this basic difference will be it does not have a turn off control. The main consideration of the structures of the internal control operating the power circuit of the TCSC to ensure immunity to the subsynchronous resistance. So, that is something we require to ensure. Here we are going to discuss the two basic philosophies. One is to operate the basic phase lock loop from the fundamental component of the line current. In order to achieve this, it is necessary to provide substantial filtering and remove the super and in particular subsynchronous component from the line current. So, we have to do the notch filtering. At the same time, maintain the correct phase relationship for the proper synchronization. And this arrangement of the conventional technique of converting the demand of the TCR current into the corresponding delay angle, which measured from the peak of the fundamental line current, is been ensured. The reference of the demand of TCR is usually provided by regulation loop of the external control, which compares the actual capacitive impedance or the compensating voltage to the reference given for the desired system of operation. So, this is the internal control of the TCSC as well as the TSC. Ultimately, you got Vc reference, from there you can have a actual X or actual Vc, whatever may be. It can have a two mode of operation, impedance mode and the voltage mode. So, you have a PI controller. So, ultimately you calculate IL. So, you got a PLL, current to the delay angle computation will be there, how much accordingly there will be a calculation of IL that is based on alpha, and from the PLL actually it will generate the delay, that will be theta plus alpha. This angle will be fed to the gate pulse generator, and it will ensure also that current does not contain any subsynchronous and the supersynchronous component of the line current, and this value will be, this information will be fed to the delay angle to operate this TCSC as well as TSSC. Thus, what we can conclude, the second approach also employs PLL synchronized with the line current for the generation of the basic timing reference, and this method the actual zero crossing of the capacitor voltage is estimated. So, it is more foolproof from the prevailing capacitor voltage and the line current by an angle correction, and thus you can actually take a computative action to DC offset. The delay angle is then determined from the desired angle, and the estimated correction angle is also to make the TCS conduction symmetrical with respect to the zero crossing, and this way we remove the zero crossing. Thank you for your attention. We thus conclude our discussion on the series controlled series fax devices, and we shall next class we shall start with the phase engaged regulator. Thank you.